we need to get started. Okay. I feel like I'm a cop. Okay, so our next speakers, I think most of the people in the room know Jim Handy and Tom Coughlin. Jim Handy is an analyst. What's that? Click and clack. Yeah, they're always at that. They're Siamese. Everyone knows it. It says maybe not everyone knows, but they're really Siamese twins. So you know so the Tom and Jim show is next. Jim Handy is an analyst. Actually, they're both analysts. Tom is also a producer of a few conferences every year. We just, in fact, we had a great panel on his storage visions a couple weeks ago in Las Vegas, you know, in conjunction with CES. And Tom was invited me to pull together a panel. We had a great panel there. But anyway, so I don't think that they need any more introductions. So Jim Handy, and not to be confused with Jack Handy in Deep Thoughts, you know, from Saturday Night Live. Jim Handy and Tom Coughlin.
Thanks, Jim. Am I on?
I can't hear you.
Yeah, it's. Oh, yeah, it's turned off. Okay. There, that's probably better. Yes. So thanks to Jim Pappas for this. The way we've got this set up is I'm going to talk for the first half. Tom's going to talk for the second half, and you know, we'll just go from there. It's a presentation though about future memories and, you know, what are the opportunities for those. So what we're going to talk about is the big changes that are coming to memory and storage. I'll talk a little bit about scaling limits and you know, what it means when we can't make transistors any smaller in storage areas. And then talk about new storage hierarchies and where these things that you've been hearing about this morning fit. I'd like to say that if you think SSDs changed everything, you just wait for what happens in the future. We'll be talking a little bit about adding more layers to the memory hierarchy, and then how processors will have to adapt to this. So first, let's talk about scaling limits. And I didn't give credit for this photography, but it is not stolen from the web. It actually was taken by Tom Coughlin, who's an avid photographer.
If you want to know why, ask me.
This is a very simple slide that I've been showing for a long time now. Rick Colson talked about using semi-logarithmic charts, and you know, I think Jim actually said some stuff about, you know, having something that was a foot high versus something that took you into the von Karman zone. I do about the same thing, but I have a different explanation as to why I do it, and that is that when you have constant growth, like 30% per year cost decline, which is what Moore's law is, then you end up with a constant rate of decrease. It looks like a straight line on a semi-logarithmic chart, and so that's why I use them. And so this is basically just Moore's law, and this is a hypothetical, something that I put together several years ago to say what happens when NAND Flash reaches a scaling limit. And this was before 3D NAND was even introduced, that I put this together. And it was just assuming that I think it was 8 nanometers, somewhere around there, 10 nanometers was the limit of how far flash memory could go. Then what would happen after that? And that was when new memory technologies were expected to come in. All of these new memory technologies that you hear about, MRAM, ferroelectric memory, and that sort of stuff, have been kind of waiting for the end of scaling to happen for the established technologies. The established technologies are being manufactured in high volume. They've had an awful lot of work put into getting their costs down, and so these new memories can't really compete on cost. And so in this slide, the black line, which is a new memory, shows what happens when you've got a wafer that costs twice as much as a NAND Flash wafer. So it doesn't look like an awful lot of a difference because of the fact that this is a semi-logarithmic chart. But what happens is once NAND Flash, the red line, reaches its scaling limit, then all of a sudden, if you took it to future process technologies and invested the money to do that, you wouldn't get any cost out of it. And that's where these new memory technologies have the opportunity to take over. Is usually, it looks like from this chart, if you have a wafer that's about twice the cost of a conventional NAND Flash wafer, and you are able to scale it past where NAND Flash stops scaling and actually take it down 2 process nodes past that, then you end up with some memory that is cheaper per bit than NAND Flash is. And so that's why everybody's been working on these new memory technologies. That's the focus, has been going past NAND Flash once it reaches its scaling limit. This is an Intel slide from some years ago showing a number of different technologies that they were looking at to do this. And the point of this slide is not to enumerate every single one of these technologies, but it's just to say that there are a lot of choices out there. You don't just have ferroelectric memory. You have ferroelectric and organic ferroelectric memory. You don't just have MRAM. You've got STT, you've got toggle mode MRAM, you've got the bizarre kind of MRAM that is worked on by Crocus, and a number of other technologies. And so, for all of these technologies, there are a lot of options. With these different options, then you get different performance, and I wanted to show how they stack up against standard conventional memories. And so this is a very subjective kind of a chart. Across the top, you've got today's memory technologies. So you've got SRAM, DRAM, mask ROM, E2 PROM, NOR, and NAND. And then you've got various attributes of all of these memories along the side. And you can download these slides later on. I'm not going to go step by step through each one of these. But what I want you to focus on is that the green is where one of these technologies is good. The yellow is where it's maybe and then the red is something you've got to put up with because of the fact that the technology is not doing what you want it to. So, for example, with SRAM, it's got a high price per gigabyte. It's got a very high active power. With DRAM, it's got kind of medium active power. It's got a very high sleep power. You can't really do an awful lot to cut down the amount of power that the DRAM is doing. Move over to mask ROM, it's very inflexible. And, so NAND Flash has got its own set of red attributes. But the big deal is cost. Very low cost for a NAND Flash. You've got kind of a low cost for DRAM, and so because of that, you've ended up finding these things in an awful lot of applications. Now, when people have been working on all these alternative memories, and the first that I was exposed to any of them was probably 1987, so it's been a long time that they've been doing it. Intel published their first PCM paper in 1970. All of these technologies have a lot more green on the chart. So this is the exact same chart on the first column on the left, but it's got different technologies placed across here. You've got MRAM, resistive RAM, FRAM, and PCM. I added something that is just my conjecture on 3D Crosspoint on here. And where it fits with that, I'm not sure where that is. Intel's really not telling much of anything. I had some people approach me during the break and just say, well, Intel's not saying anything. They will in time. But what's important with all of these technologies is that still they're a higher price per gigabyte than the entrenched technologies. And that's what's been holding them back. Even though they're technically superior, they've got this cost issue. And I like to say that my background is that I'm an engineer with an MBA, which is kind of an unfortunate combination because it means that I fall in love with the technology and then I find out that it's not cost effective and so nobody can use it. And that's been the problem with these technologies since the 1970s, since the 1980s. They've always been far more expensive than what's entrenched. And so people do all of these very strange contortions to be able to use DRAM and NAND Flash in a cell phone without killing the battery in the first 40 seconds that the cell phone is turned on. It takes a lot of software contortions to do it. But the problem with these technologies is that they've been looking to replace entrenched technologies rather than looking to augment them. And that's something I'm going to talk about in just a minute. Because we're going into new storage hierarchies. Isn't that a pretty picture? But we're going to be following a path that we've followed before. Now I'm going to make Jim Pappas, I'm going to one-up Jim Pappas because I'm going to show you a chart that is a log chart. Yay!
Ooh, 2 logs.
Okay, so this is price per gigabyte across the bottom, and it's bandwidth vertically. And this is more a conceptual chart than anything, and a lot of people in this room will have seen this before because I tend to drag this thing out an awful lot when I'm using it. What it shows is it shows all the different layers of the memory hierarchy in a system. And so before we had SSDs, then we had L1, L2, L3 caches. You know, maybe there were some of those, maybe there were other ones. You know, as time has progressed, we've gotten more caches inside the processor. They're the fastest, or I'm sorry, they're the most expensive thing, and they're also the fastest, so that puts them up into the corner. DRAM then came next, and then after that, hard drive and tape came later. Now, over time, hard drive and tape got cheaper and just continually got cheaper, but they didn't really do an awful lot to increase speed. And with all of the semiconductor technologies, thanks to what's called Dennard scaling, as the processes shrank, then they got faster and faster. And so because of that, you had everything in the top 4 orbs, DRAM and all those caches, getting faster and cheaper. And at the same time, the other technologies were getting just cheaper. And that opened up a gap between those 2 areas. Now, NAND Flash ended up filling that gap once those guys moved apart over time. And we've got a similar kind of a situation going on now. Something kind of odd about NAND Flash is that it uses quantum tunneling to move electrons onto and off of the floating gate. That's something that you can't speed up with Dennard scaling. And so because of that, the NAND Flash is actually getting cheaper but no faster. And all of these other technologies are still getting cheaper and faster. And so you can tell that there's going to be a gap that opens up. But the reason why NAND Flash fit into this hierarchy was because of the fact that it became cheaper than DRAM. Something that I want to say about this too is that I put all of these in a line because to the application program, if it's not down there managing storage by itself, then all of this looks like one big continuum. It just looks like a big DRAM, or it looks like a very fast hard disk drive that's accelerated by these different layers. And so because of that, you know, a lot of existing technology can be used without all of these new programming methodologies, but they can't be used to their best advantage. Also, I should say, the reason why I use a Loglog chart was not to frighten anybody, but it was because if I took this chart and I turned it into a linear chart, then you'd end up with a huge L1 bubble, and then you wouldn't even be able to see any of the other bubbles because of the fact that they'd be all squished down into the corner. Okay, so the phenomenon that made SSDs get into this space was that NAND Flash became cheaper than DRAM. Up until 2004, NAND Flash was great for storing digital pictures on cameras and doing USB flash drives. But then in 2004, when NAND Flash prices became lower than DRAM prices, then we ended up with this same thing that I just showed you in the prior slide. You had NAND fitting between DRAM and hard disk drives as far as where it went cost-wise in the memory hierarchy. And the speed was already there. So we've got the same thing that we're approaching now with 3D Crosspoint. If you move those upper orbs up and to the right, up and to the left, I'm sorry, and if you move the NAND Flash hard drive and tape across just to the left, getting cheaper but no faster, then you open up a new gap. And so that's where 3D Crosspoint really fits in. That's what my MBA side says is going to drive it into preeminence, and whether or not people really understand how to use its persistence doesn't really matter so much. What really matters is that it adds a new layer that allows you to get cheaper and it allows you a better cost performance ratio in your PC. You can now actually cut down how much DRAM you use in your computing system and still increase the memory size. And the net effect of that is that it makes your SSD accesses look like they're faster in this hierarchy. And with that, I'm going to turn it over to Tom Coughlin, and he can talk a little bit more about these new technologies.
Thank you, Jim. And my mic is working. That's wonderful. So we saw a version of this slide before, so Intel has talked about this 3D Crosspoint technology. They still haven't yet told us what it is. but we're supposed to start seeing some products this year. So I'm not going to dwell on this slide because they already had people go through it. And also, we already had people go through various versions of this, so we don't need to talk too much about that as well, except that the idea here is that we can go from interface improvements, or as we go from hard drives to SSDs, we can get improvements that are basically due to the device. Now we're trying to scale down to the interface and the software in order to get performance that's closer to the actual device performance, especially moving from NAND into this 3D Crosspoint, or for that matter, any of the other technologies. Because in a sense, Jim showed that table earlier, there's a lot of alternative technologies out there, and a few that weren't even on that table. We are kind of at a Cambrian explosion of memory and storage technologies, where there's just so many alternatives that are out there, being pushed by different companies. They have different kind of capabilities, and it's really going to be interesting how this all shakes out. It's likely that we're going to see more than one technology in use for some time to come before we get to that perfect world of maybe two classes of storage. And I'll get into a little more why that happens in just a minute here. But here's some projections from a report that actually Ed Grachowski and I did last year on emerging non-volatile memories, and where we're looking at projections of annual shipping capacity for, you can see the DRAM, NAND Flash, because of the price and its many applications, it's higher shipping capacity. We're showing some impact that we project in the future on the SRAM in particular, due to probably could be the MRAM, spin tunnel torque MRAM. Also showing an estimate of the introduction of Crosspoint, which will probably have some impact on DRAM and possibly on SRAM as well. Now let's talk a bit about, again, we've got all these alternatives. So let's talk about how we build this Dagwood sandwich of future storage systems and devices, because that's really what it's liable to look like with all these things out there and all these people that are going to be pushing these different technologies. So there's again, it's in this report that Ed and I did, but there's some work I did with Steve Hetzler, who's a fellow at IBM, and I think he's even talked at some of these SNE events before, where we're looking at a concept called the touch rate, which is that, again, stay, just like Jim said, in the log-log scale. We've got something here on the vertical axis called the touch rate, which is the number of times you can touch all the content on a device within a given period of time. In this case, it's touches per year. That's how many times you can touch every piece of information on that device in a year's time on a log scale. We also have something called response time. From when I ask for some data, whether I'm writing or reading that data, to when I get that data and it's ready to take the next command. So that's the response time. So they're both log scale. And what we've plotted here, going basically from the lower left to the upper right, we've got first of all, if we go up the axis, we've got more accessibility. We can touch more of the content in the drive. As you go to the right here, we get faster. Our response time gets smaller. So in the lower left, we're in what's called an inactive region. I can't get to this stuff very, very fast, and I can't, and the response time is fairly slow. And that's the left-hand side there. As we move to the right, we get into what we're calling a cold archive region, and then into a semi-active, and then a nearline, finally a transaction processing, and up and into the upper right-hand is a high IOPS region, a lot of which is served today by volatile memory. And that's where these non-volatile memories are going to eventually fit into. A lot of them, as well as into the transaction region. So let's see then how we can map various types of storage devices, ones commonly used today, not all these new funny animals that are out there and coming in the future. So we see at the lower left, tape fits into that inactive region, and we have a cold archive region. Tape can be there, but also capacity hard drives. Performance hard drives on top of that, flash memory on top of that, and finally there's that region up in the corner, which is this very high ops region. That's where today's volatile, tomorrow's non-volatile memories will live. And we can see how that fits into this response time and the touch rate. They all have this interesting shape to them because as we increase the size of the objects that we're moving around, we saw those charts earlier, we were talking about 4 kilobytes or 64 bytes, for instance. That's the size of the things that they're moving. As those increase, we sacrifice response time to get better touch rate, to be able to access more of the data on the device in a given period of time until we reach a saturation point. So it has this L-shaped curve, or J-shaped curve, however we want to look at that these devices have. And likely, though we haven't seen any data on that, so will the new technologies, because this is an inherent characteristic of these kind of devices. So if we actually then map on some real products into this kind of a chart of touch rate versus response time, we can see that here we have a capacity hard disk drive. It's a hard disk drive that is focused on giving storage capacity. It's for lower cost type drive. And you can see that if we start out with, say, 4 kilobyte, we have very fast response time for 4 kilobyte objects. We move around, but we can't, with our touch rate, our ability to touch all the data on the drive is fairly low. If we increase the size of that up to a point, say up to, say, 1 megabyte type content or pieces of data that we're moving around, now although we sacrifice a little bit on response time, we gain an awful lot on that touch rate. So I can access more of the data on the device. After that point, it starts leveling off. Even if I go to larger size objects that I'm moving around, my ability to touch the data doesn't improve and my response time suffers. So the optimum point is somewhere around the knee of these curves. Also, if we look at the performance hard disk drives, Stace performance hard drives, right there you can see the same kind of curves. And if we go then to 2 solid state drive cases with flash memory at this point, we can see an eSSD and a PCIe shown up here. And we can see that they follow a similar sort of curve, although now they're higher because they're smaller capacity. They're higher on the touch rate, the ability to touch all the data, plus that's combined with faster speed. So altogether, that gives you a high touch rate. And you see the same kind of characteristic there. Now, although it's not going to go into depth in this, the interesting thing about this is that you can also think about odd things, like if I have a large enough capacity device, which we're not very far away from, whether it be an SSD or a hard disk drive, where my access speed can't allow me to get all the data, it's possible to build a device that I can never write or never read all of the data on it within its lifetime. So, interesting aspects of looking at this stuff. And by the way, Steve Hetzer is going to be doing a version where he's going to be looking at this more for system performance design characteristics at the next Storage Valley Separate Club on February 18th, if you're interested in that. So let's talk a bit about where this fits in, how all this stuff may affect the way we do processing, because that's why we're doing this in the first place. We saw this chart before where these new persistent memory devices that we're talking about here, whatever they are, they're so fast, they can now become an integral part of either a DIMM-based or even internal memory within these devices themselves, if they're compatible with the rest of the processes. The implications are that we can retain data during power loss within the system itself. So therefore, we can have instant recovery if the power goes down. We have lower latencies than hard disk drives, lower power than DRAM. We can have persistent states that allow interesting architectures that allow, for instance, remote direct memory access between processors, especially with some of these fabric technologies people are talking about. Ultimately, we can support logic and memory architectures, which could lead to new distributed computing approaches to computing that we could be doing in the future. So in summary, the scaling limits that Jim was talking about open the doors to new memories, new architectures to create other opportunities. We basically have a great plethora of things that are out there, going to be here for at least the next few years as possibilities. It'll be interesting to see how they evolve. NAND is now, 3D Crosspoint and other technologies are coming out. Performance drives the need for new layers of storage. And these new storage layers will drive new processor architectures, and application programs and the software, as pointed out earlier, will need to be developed in order to enable this capabilities. So with that, I want to thank you very much. And I guess we can take, do you have time for some questions?
2 minutes.
2 minutes, okay.
2 minutes.
Any questions?
I think we put them to sleep.
I guess so. Okay, click. All right, you get some time back, Jim.
Okay, so next is our first panel of the day. So if our panelists could come on up. We have Matt Bryson is going to be the chair or the moderator for this panel, so give us a second to set up. And so Jim and Tom just talked about the various types of memories and different tiers and multiple new NVM types of technologies. I think this panel is going to go through and talk about some of these new technologies that are coming by. Earlier we talked about the fact that all of this work that we're doing in the SNIA NVM programming model was all kind of contingent. We're forward-looking and saying that at least one of these technologies would win. Maybe all of them do succeed.